Today I have the 2.5 square theorem for you. This says that if p is a prime number, there must exist integers a and b such that a squared plus b squared plus 1 is 0 mod p. So in other words, a squared plus b squared plus 1 is a multiple of p. Now, why have I called this the 2.5 square theorem? Well, that's actually more as a joke of the TV show 2.5 Men, but also because this is closely related to the 4 square theorem, or Lagrange's 4 square theorem, which says that any positive integer can be written as the sum of 4 square numbers. And in fact, this result here can be used kind of like a lemma to prove Lagrange's 4 square theorem. And I'll discuss that closer to the end of this video. Let's dive into a proof of this lemma, or this 2.5 square theorem. This is pretty clearly true if p is the prime number 2. I mean, if p is 2, we can just say 1 squared plus 0 squared plus 1. That's going to be 2, and that's congruent to 0 mod 2. So we may as well assume that p is an odd prime. So if p is an odd prime, we can write it in the form 2n plus 1. Okay, cool. What we're going to do is consider two different sets of numbers. The first set I'm going to call A, and it's going to consist of the numbers alpha squared, for which alpha is just any number between 0 all the way up to n. So it's just a set of square numbers from 0 up to n squared, where n is this n here in p, which is, well, p is 2n plus 1, so n would be p minus 1 over 2. Okay, so that's what A is. And I'm going to define a set B as well. Very similarly defined. It's going to be the set of minus beta squared minus 1, for which beta is 0, 1, all the way up to n. So both of these sets have n plus 1 numbers in. Okay, here's some observations. Firstly, A intersect B is going to be the empty set. Why is this? Well, clearly, these guys are all going to be non-negative. These guys are all going to be strictly negative. Hence, there's not going to be any intersection. Okay, what else can we observe? Let's look at A. Let's say we have two different elements in A. Let's say x squared and y squared are in A, and let's suppose that they are the same mod P. So suppose we have numbers x squared and y squared in A with x squared equals y squared mod P. Now, if this is true, then we get x squared minus y squared, which we can write as the difference of two squares. So x plus y, x minus y. This is going to be 0 mod P, just by subtracting the y squared here. Okay, so that just tells us that x plus y times x minus y must be a multiple of P. But since P is prime, that must mean that either this guy is a multiple of P, or this guy is a multiple of P. So let's look at x plus y. Now, x plus y cannot be a multiple of p. Why not? Well, x plus y, I mean, the only way it could be a multiple of p is if both x and y are 0, in which case x plus y is 0, which is a multiple of p. But if at least one of them isn't 0, if you take two numbers from this set and add them up, it will be a positive number, but it will be at most 2n, which is less than this prime number p. So x plus y will be a number between 0 and, or between 1 and 2n. And so this guy here can't be a multiple of p unless x equals y equals 0. Okay, what about x minus y? When is that a multiple of p? Similar reasoning, because we've got only 0 up to n, the smallest that x minus y, this will be some number between minus n and n. And the only number in that range, which is a multiple of p, is the number 0, which occurs when x equals y. And so the only way that x squared minus y squared can be 0 mod p would be if x equals y. And so therefore, what this tells us is that every single number in A has a different residue mod p. So if you take two elements from A, two square numbers from A, and you subtract them for, and those two guys are the same, then those two things must have been if they're the same mod p, then those two numbers must have originally been the same. So every single number in A is distinct mod P. For the exact same reason, we get the same result in B. Every single number in the set B is distinct mod P. Well, how can we use this? Well, let's look at the set C, which I'll just squeeze in here. C is just going to be defined to be A union B. So everything in A along with everything in B. Firstly, how many elements does C have? Well, C is going to have 2n plus 2 elements because this guy has n plus 1, this guy has n plus 1, and the intersection is empty. Okay, cool. And now we're going to use the pigeonhole principle. P, remember, is 2n plus 1, but C has a 2n plus 2 elements. So P is 2n plus 1, C has 2n plus 2 elements. So by the pigeonhole principle, since there are precisely 2n plus 1 residues, mod P, there must be at least two numbers in C which have the same residue. So there must exist, let me use gamma and delta in C, where gamma is equal to delta mod P. But here's the thing. We know, as we just mentioned, everything in A is distinct mod P from one another within that set. And similarly for B, everything in there is distinct mod P. So for there to be two guys in C which are the same mod P, precisely one must be from A and one must be from B. So that must mean there's some alpha squared, so maybe I call it A squared, that's in A that's equal to some B in B. So that would be minus B squared minus 1. And this is mod P. And now we just need to add B squared plus 1 on both sides. So we get A squared plus B squared plus 1 is congruent to 0 mod P. And that is exactly what we set out to prove. So we've proved that A squared, or that there exists these numbers, A squared plus B squared plus 1 is 0 mod P. And that proves our lemma, or our 2.5 square theorem.
Pause! I've decided to set up my own tutoring company to help you study maths at a top university. So if you like the way I explain things, go check it out. Let's get on with the video.
I also mentioned at the start of this video, this can be used in the run-up to the 4 square theorem, proving that every integer or positive integer is the sum of 4 square numbers. How do you go from this 2.5 square theorem up to the 4 square theorem? Well, I'll leave the details for you to check over, but essentially what you firstly do is prove that every single prime, for every prime p, you can write p as the sum of 4 squares. So for every prime p, there exists a squared plus b squared plus c squared plus d squared. The way you do this is, well, it's pretty clear that mp, where m is some positive integer, there is some positive integer m, sorry, that m times p is the sum of 4 squares. That's pretty much by this result here. I mean, if I just add 0 squared here, I get that a squared plus b squared plus 1 squared plus 0 squared is m times p, is a multiple of p. And so we have that. And then what you do is say, okay, there exists some m, so we may as well take m to be as small as possible. And it turns out then that m has to be 1, and you can prove that by contradiction. So then you have that any prime can be written as the sum of 4 squares. And now that you've got this, you have to apply one of Euler's identities, which basically says that x squared plus y squared plus z squared plus w squared times a squared plus b squared plus c squared plus d squared equals, and I won't bother writing it out, but it equals something squared plus something else squared plus something else squared plus something else squared, all in terms of a, b, c, d, and x, y, z, and w. And basically what this tells us is that if you have two numbers, let's call this number here x, and this number here a, if you have two numbers x and a, which can be written as the sum of 4 squares, then their product can also be written as the sum of 4 squares, because these guys are 4 square numbers. And so, for example, now that we have that all primes can be written as the sum of 4 squares, that also allows us, for example, to prove that the number 6, can be written as the sum of 4 squares, because 6 is 2 times 3, and we can write 2 as the sum of 4 squares and 3 as the sum of 4 squares. And we can kind of repeat this process inductively to prove that any positive integer must be able to be written as the sum of 4 squares. So it's a pretty nice proof. I encourage you to either attempt these details for yourself or do some research and learn about them. But just so this video doesn't get too long, I will leave it there for today. Thanks for watching. Have a great day.